Hello, and thank you for joining me on this journey. Tonight, we will slowly drift into vast cosmic voids, immense regions where galaxies grow rare and space stretches across millions of light years. Imagine floating between faint clusters of light, where the universe forms a delicate web and wide openings quietly expand over time. Early astronomers once believed the cosmos was evenly filled, but as they mapped distant galaxies, these hidden gaps began to appear, revealing a deeper structure shaped by gravity and the unseen presence of dark matter. If you enjoy these relaxing moments, please consider leaving a like, subscribing, and turn on all notifications so you don't miss any of our future videos. But for now, just breathe. Let your body relax, release any tension, and allow your mind to drift. Let's begin. In the early decades of the 20th century, astronomers peered into the heavens with instruments that were, by modern standards, modest yet remarkably revealing. Through these lenses, the night sky revealed a tapestry of luminous points, each a distant galaxy, each a collection of stars, gas, and dust, stretching across unfathomable distances. Initially, scientists anticipated a universe of gentle uniformity, a vast expanse where galaxies were sprinkled in patterns as regular as grains of sand on a beach. The expectation was simple. Space would be filled, a cosmic canvas without the stark interruptions of emptiness. Yet, as the painstaking observations accumulated, subtle anomalies began to emerge. Certain regions of the sky seemed curiously underpopulated. Amid the clusters and swirls of galaxies, there were stretches where starlight appeared scarce, where the maps hinted at invisible expanses beyond the reach of telescopes. These nascent clues pointed to something unexpected: absence, a shadow of missing matter lurking between the luminous islands. It was a whisper of emptiness that invited contemplation, a question without immediate answer, hinting at a deeper complexity in the cosmos than anyone had imagined. Advances in measuring cosmic distances deepened this sense of intrigue. Through Redshift, astronomers could infer how far galaxies lay from our vantage point on Earth, revealing a three-dimensional structure of staggering scale. When these distances were plotted, patterns began to emerge, regions of dense aggregation juxtaposed against vast, seemingly barren spaces. The gaps were not merely occasional. They spanned millions of light years, forming the earliest glimpses of what would eventually be recognized as cosmic voids. These discoveries unsettled long-held assumptions. If the universe was meant to be smooth, why were these voids so pronounced? Scientists began to consider that emptiness itself could be meaningful, that the absence of matter might sculpt the cosmos as decisively as the presence of stars and galaxies. Each map became a puzzle, each void a silent testament to forces at play beyond immediate observation. The very notion that nothingness could hold significance challenged conventional thinking, calling for a shift in perspective that would unfold over the coming decades. The methodology of observation was deliberate, almost meditative. Telescopes scanned the heavens, night after night, recording positions, brightness, and spectral lines, the faint redshift of distant galaxies revealing their recessional velocities. Patterns were not immediately obvious, requiring patience and meticulous analysis to discern the intricate fabric of cosmic distribution. Every survey, every measurement, carried with it the faint hint of the unknown, the suggestion that the universe was far more intricate than a mere scatter of luminous points. In these early maps, one could sense the universe as both intimate and immense. The dense clusters of galaxies formed knots of matter, gravitational anchors holding the surrounding stars and gas in place, while the voids extended like valleys between mountains, dark and profound. These underpopulated regions were not empty in a simplistic sense. They were spaces defined by their scarcity, realms where the familiar rules of galactic congregation yielded to subtle, unseen forces. As researchers compiled more comprehensive charts, the scale of these voids became increasingly apparent. Some spanned tens of millions of light years. Others hinted at far larger expanses yet to be fully explored. Their discovery marked a subtle but profound turning point in cosmology, suggesting that the architecture of the universe could not be understood solely through what was present. In the vast interplay of matter and absence, the cosmos revealed a new narrative, one in which emptiness itself could guide the formation of galaxies, influence motion, and shape the large-scale structure of space. Thus, the first glimpses of emptiness opened a doorway to an entirely new realm of understanding. Astronomers were no longer merely cataloguing stars and galaxies. They were tracing the invisible contours of the universe, feeling the pull of unseen forces through the silence of underpopulated expanses. These early observations set the stage for a revolution in cosmology, hinting that the voids were not anomalies, but integral threads in the grand weave of the cosmos. Here, in these subtle absences, lay the first intimations that nothingness could be as compelling, as essential, and as revelatory as the clusters of light that first drew humanity's gaze upward. Long before the intricate architecture of the universe became clear, cosmologists imagined space as a smooth, almost featureless expanse. Matter was thought to be evenly distributed, a tranquil sea stretching in every direction, unbroken by vast voids or complex patterns. Early observations seemed to support this notion, offering charts where galaxies appeared scattered with gentle regularity. Yet, as instruments grew more sensitive and surveys more extensive, subtle irregularities began to accumulate, hinting at a hidden complexity beneath the apparent simplicity. Evidence began to emerge that galaxies were not sprinkled randomly. Instead, they traced extended filaments and clusters, leaving enormous stretches where few stars or galaxies resided. These underdense regions, once thought to be exceptions, appeared systematically in the maps, revealing a cosmos of intricate structure rather than uniformity. The emerging vision resembled a three-dimensional web, with luminous strands and nodes threading through vast darkness, shaping the large-scale distribution of matter. The idea of a cosmic web represented a profound shift in understanding. It suggested that the universe had evolved from tiny variations in density, amplified over billions of years by gravitational attraction. Dense regions became hubs where galaxies accumulated, while lower density zones expanded, forming the vast voids observed today. Gravity, acting across immense scales, organized matter into an elaborate pattern of filaments, walls, and bubbles, each stretching across hundreds of millions of light years. This perspective linked the distribution of galaxies directly to the underlying physics of the early universe, suggesting a continuous narrative from primordial fluctuations to the present-day cosmic architecture. Computer simulations and theoretical models began to reflect this complexity. By inputting the properties of dark matter and ordinary matter, cosmologists could recreate the formation of a web-like structure, observing how tiny initial differences could grow into vast networks of filaments and voids. The simulations showed galaxies collecting along these threads, while enormous underdense regions expanded in response to surrounding gravitational forces. Within this framework, voids were no longer anomalies. They were natural consequences of structure formation, as essential to the universe's composition as the clusters themselves. Observational evidence reinforced these models. Surveys extending across billions of light-years, including pioneering Redshift projects, revealed the sponge-like configuration of the cosmos. Filaments connected massive clusters, stretching across seemingly empty stretches of space, while supervoids emerged in the gaps, vast and sparsely populated. These structures suggested a universe both dynamic and ordered, sculpted by forces that were invisible yet decisive. The contrast between dense clusters and immense emptiness revealed a delicate balance, showing how matter flows through cosmic highways while leaving other regions largely vacant. The implications extended beyond mere mapping. The cosmic web provided insights into the distribution of dark matter, the invisible scaffolding that guides the formation of galaxies. Observed patterns of galaxy clustering matched predictions of simulations incorporating dark matter, confirming its pivotal role in shaping large-scale structure. Furthermore, the arrangement of filaments and voids reflected the imprints of the universe's earliest moments, capturing the faint echoes of primordial fluctuations now magnified across billions of years. In this view, the universe was neither chaotic nor monotonous. Its complexity arose from an elegant interplay of forces, gravity drawing matter together, dark matter structuring the framework, and initial density variations dictating the growth of clusters and emptiness. Voids emerged as a natural counterbalance, defining boundaries for filaments and influencing the motion of galaxies along their edges. Each filament traced a path through space, bridging clusters, while the intervening emptiness accentuated the contrast, revealing the full intricacy of cosmic organization. Through this evolving understanding, the paradigm of a uniform universe gave way to a vision of remarkable intricacy. The cosmos became a dynamic web where matter and absence coexisted in complementary harmony. The recognition of voids transformed them from curiosity to fundamental elements, shaping not just local structures, but the grand geometry of the universe. In tracing these threads, astronomers began to appreciate that the vast network of galaxies and emptiness was a story written in both presence and absence, an unfolding narrative of formation that would guide all subsequent exploration of cosmic structure. A revolution in understanding the cosmos emerged with the ability to measure galaxies not only across the sky, but in depth, revealing the three-dimensional geometry of the universe. Early sky surveys provided two-dimensional projections, offering a flattened map of positions, but concealing the vast separations between distant systems. Redshift, the stretching of light as galaxies recede, transformed these maps into immersive spatial representations, allowing astronomers to perceive the universe as an interconnected network of matter and emptiness. The introduction of large-scale redshift surveys marked a decisive turning point. Projects like the CFA Redshift Survey meticulously catalogued thousands of galaxies, assigning distances through their spectral shifts. These data revealed striking patterns. Galaxies were not scattered haphazardly, but aligned along elongated filaments, converging in dense clusters and leaving immense underpopulated regions in between. The emerging three-dimensional structure displayed a complexity that had only been hinted at in earlier two-dimensional charts, transforming the notion of cosmic distribution into a tangible, measurable form. Visualizations from these surveys painted a compelling picture. Filaments appeared as threads of luminous matter, sometimes stretching hundreds of millions of light years, curving and intersecting in intricate arrangements. At the nodes, clusters of galaxies gathered like beads on a cosmic string, while the spaces between, vast voids, spanned similarly staggering distances, often containing only a sparse sprinkling of galaxies. These voids were not anomalies or errors in measurement. They were persistent, reproducible features, confirming that emptiness itself is an intrinsic element of cosmic structure. Advancements in observational technology amplified these discoveries. Instruments capable of capturing spectra with unprecedented sensitivity expanded surveys to include millions of galaxies. The Sloan Digital Sky Survey, for instance, extended the reach of previous catalogues, producing maps that traced filaments and voids with remarkable clarity. Researchers could now see not only the distribution of visible matter, but infer the gravitational influence of unseen components such as dark matter, which guided galaxies into filamentary patterns while allowing voids to expand. Each new dataset reinforced the notion that the universe's structure arises from a combination of initial conditions, gravitational forces, and the influence of invisible mass. The geometry revealed by Redshift mapping has profound implications for understanding cosmology. Filaments, acting as conduits for matter, influence the motion of galaxies, shaping their velocities and trajectories. Clusters, dense with stars and gas, dominate local gravitational fields, while voids exert subtle, expansive effects, providing regions where matter is comparatively scarce. Together, these structures illustrate the dynamic interplay between gravity, dark matter, and the expansion of space itself, capturing the universe's large-scale architecture in a way that was previously inaccessible. Redshift surveys also offer a lens into the universe's history. By measuring the distances of galaxies, astronomers effectively observe light that traveled across billions of years, allowing them to trace the evolution of structure over cosmic time. Filaments and clusters form gradually from tiny initial density fluctuations, while voids expand as matter flows outward toward more concentrated regions. The three-dimensional maps reveal this growth, showing the universe as a living, evolving network where emptiness and presence are inseparably entwined. Beyond the scientific implications, the aesthetic of the cosmic web is striking. The interweaving of luminous filaments and deep voids presents a grand, almost architectural order, a vast lattice of matter sculpted across the observable universe. Observers can trace paths through these structures, following the alignment of galaxies along filaments, or contemplating the enormity of the voids that punctuate them. These maps make the abstract tangible, translating the invisible gravitational scaffolding into patterns that can be seen, measured, and understood. The realization that voids are fundamental rather than incidental reshaped cosmological thinking. They are critical to understanding how galaxies cluster, how matter flows, and how the universe expands. Redshift surveys provide not only empirical evidence of these structures, but also a framework for testing models of cosmic evolution, linking theory with observation in a precise, measurable way. In revealing the universe in 3 dimensions, these surveys transformed the perception of space itself, showing that the emptiness between stars and galaxies is not a void in knowledge, but a central element in the story of cosmic formation, guiding our understanding of the universe's architecture across vast scales and epochs. In 1981, astronomers stumbled upon a cosmic region so vast and sparsely populated that it challenged every prior assumption about large-scale structure. Nestled within the constellation Boötes, this enormous expanse, later named the Boötes Void, stretches roughly 330 million light-years across, making it one of the largest known voids in the observable universe. Its discovery emerged from Redshift surveys designed to map galaxy positions, revealing a space almost completely devoid of the luminous matter that dominates surrounding regions. The emptiness was startling. Not a mere gap, but a supervoid that dwarfed ordinary cosmic structures. Observations confirmed the Boötes Void contained only a few dozen galaxies within a volume where thousands might have been expected. These galaxies appeared scattered and isolated, like distant lanterns in an immense dark sea. The surrounding universe, in contrast, displayed intricate networks of filaments and clusters, emphasizing the stark contrast between dense regions and the profound emptiness of the void. Its boundaries were gradual rather than abrupt, with galaxies becoming increasingly sparse toward the interior, offering a subtle transition from structure to expansive underdensity. The discovery prompted immediate questions about cosmic evolution. How could such a vast region remain nearly empty in a universe governed by gravity? Standard models of galaxy formation and clustering seemed insufficient to explain a void of this magnitude. Researchers speculated that the Boötes Void might represent the merging of smaller voids, a natural amplification of underdense regions over billions of years. This interpretation aligned with the understanding that gravitational forces drive matter toward denser clusters, allowing low-density regions to expand and coalesce into larger voids. Detailed studies of the Boötes Void illuminated its internal composition. While most of the volume is remarkably empty, the few galaxies present appear to follow faint substructures, hinting at the residual filamentary threads that persist even within extreme underdensities. These isolated galaxies offer clues to how matter can survive in vast expanses with minimal gravitational interaction. Their distribution also provides evidence that voids are not uniform hollows, but complex regions with subtle variations, shaped by both the initial conditions of the universe and the ongoing flow of surrounding matter. The existence of the Boötes Void also sheds light on the behavior of dark energy and the expansion of space. As the universe grows, voids expand more rapidly than dense clusters, their low gravitational pull allowing space itself to stretch. The Boötes Void, with its enormous scale, serves as a natural laboratory for observing these effects, demonstrating how emptiness can influence cosmic dynamics across millions of light years. Its growth is tied to the broader evolution of the cosmic web, illustrating the balance between matter aggregation and the expansion of underdense regions. Surrounding the void, filaments and galaxy clusters trace the edges with remarkable precision, creating a boundary where matter concentrates. The contrast between the void's interior and its periphery underscores the influence of gravity on the flow of matter. Galaxies migrate along filaments, pulled toward dense nodes, while the void expands in response, becoming increasingly empty. This interplay highlights how cosmic voids are not static absences, but active regions shaped by the invisible forces guiding the universe's evolution. In examining the Boötes Void, astronomers recognized that voids are fundamental components of cosmic structure rather than anomalies. Their sheer scale affects the motion of nearby galaxies, subtly influencing velocities and trajectories. The emptiness also amplifies the effects of dark matter and dark energy, making these regions crucial for testing cosmological models. Each observation provides insights into the universe's underlying framework, demonstrating that vast voids, while appearing lifeless, hold profound significance in the orchestration of large-scale structure. The Boötes Void stands as a monument to the extremes of cosmic architecture. Its discovery reframed understanding of emptiness, showing that even the absence of matter carries essential information about gravitational dynamics, the formation of filaments, and the expansion of the universe. Within its immense expanse, the cosmos reveals that emptiness is not merely a lack of stars or galaxies, but a vital ingredient in the complex network that defines the large-scale structure of everything we can observe. The universe reveals itself as a grand tapestry, a sprawling network where luminous filaments intertwine with immense regions of underdensity, forming what scientists now call the cosmic web. From the smallest scales observable in galaxy clusters to the vast expanses spanning hundreds of millions of light-years, this structure is defined by the interplay between dense matter and expansive emptiness. Filaments trace the pathways along which galaxies migrate, while voids create boundaries that shape the flow and distribution of matter across the cosmos. Filaments, composed of dark matter and ordinary baryonic matter, serve as the connective tissue of this network. Galaxies form along these strands, gathering in elongated chains that stretch across vast distances. At intersections, clusters accumulate, gravitationally anchoring thousands of galaxies in concentrated hubs. The spaces between these structures, the voids, are not mere gaps, but fundamental components, providing contrast that allows the underlying architecture to emerge. Their presence delineates the boundaries of filaments, influencing how matter streams along these cosmic highways and shaping the velocity of galaxies as they move toward denser regions. Observational surveys have provided the empirical foundation for understanding the web's geometry. Extensive Redshift measurements, from pioneering projects to the comprehensive Sloan Digital Sky Survey, trace the positions of millions of galaxies, revealing the intricacies of the network. Filaments appear as luminous threads bridging clusters, curving and intersecting in three-dimensional patterns, while voids emerge as vast, underpopulated chambers, each with subtle internal structure. These maps confirm that the universe's large-scale organization is not random, but shaped by the forces acting since its earliest moments. The formation of the cosmic web is driven primarily by gravity, acting on initial density fluctuations in the primordial universe. Slight overdensities attracted more matter, growing into the dense nodes observed today, while underdense regions expanded, forming the voids that thread the web. Dark matter plays a critical role, providing the unseen scaffolding upon which visible galaxies assemble. Without this invisible component, the filaments would not maintain their elongated structures, and voids would not develop the sharp contrasts seen in observations. Simulations consistently demonstrate how these dynamics reproduce the large-scale features observed, showing that filaments and voids are complementary, evolving together in a delicate balance. The architecture of the web is dynamic, evolving as galaxies move along filaments and voids expand. Matter flows from emptier regions into the dense intersections, gradually reinforcing the contrast between clusters and underdense zones. This motion is subtle yet persistent, reflecting the cumulative effect of gravitational attraction over billions of years. Filaments act as channels, guiding matter along predetermined paths, while the surrounding voids stretch and grow, amplifying the structural patterns within the cosmic network. Voids themselves provide unique insights into cosmology. Their size, shape, and distribution encode information about the properties of dark energy, the expansion rate of the universe, and the overall matter content. Studying these regions allows astronomers to probe forces that operate across immense scales, revealing the subtle effects that govern the evolution of galaxies and clusters. The interplay between voids and filaments demonstrates that emptiness is not merely an absence, but an active participant in cosmic dynamics, influencing how structure forms and evolves over time. The visual and conceptual impact of the cosmic web is striking. Vast, luminous filaments weave between deep, expansive voids, forming a lattice of matter that spans billions of light years. Each element, thread, node, and empty space contributes to a coherent structure shaped by gravity, dark matter, and the initial conditions of the universe. By observing this network, scientists gain not only a clearer picture of the universe's architecture, but also an understanding of how matter organizes itself across immense scales. Through the lens of the cosmic web, filaments and voids are inseparable. The emptiness defines the threads, and the threads give context to the voids. Together, they form a framework that underpins all observable structure, guiding galaxies along intricate paths, while revealing the unseen forces that shape the universe. In studying this interplay, astronomers uncover a delicate balance, a rhythm of presence and absence that extends across the cosmos, offering a calm yet expansive view of how the universe arranges itself in patterns both immense and precise. At the dawn of the universe, moments after the Big Bang, the cosmos was almost perfectly uniform. Matter and energy were spread with remarkable evenness, creating a nearly featureless expanse. Yet, embedded within this primordial smoothness were minuscule variations in density, tiny fluctuations that would leave a profound imprint on the universe's large-scale structure. These initial ripples, recorded in the cosmic microwave background, provided a blueprint for the formation of both galaxies and the immense voids that would emerge between them. Gravity acted upon these slight differences, drawing denser regions together while allowing less dense areas to expand. Over billions of years, the contrast between high-density and low-density zones increased, producing the intricate tapestry of matter and emptiness observed today. Dense patches coalesced into filaments, clusters, and superclusters, while the underdense regions, destined to become cosmic voids, grew ever larger, shaped by the outward pull of surrounding matter. The interplay of these forces created a balance between concentration and dispersion that defined the universe's architecture. Dark matter played a crucial role in amplifying these early fluctuations. Invisible, yet gravitationally influential, it guided ordinary matter into the developing web of structure, reinforcing the separation between dense clusters and expanding voids. Without dark matter, the contrast between matter-rich filaments and underdense regions would be far less pronounced, leaving the universe more homogeneous and lacking the dramatic emptiness that characterizes cosmic voids. Simulations incorporating dark matter reproduce the growth of voids with remarkable fidelity, demonstrating how early perturbations in density evolved into the vast, interconnected network observed today. Observations of the cosmic microwave background reveal the subtle seeds of these structures. Temperature variations across the sky correspond to regions of slightly differing density in the early universe, with hotter areas representing denser zones and cooler areas corresponding to underdensities. These tiny differences, often measured in fractions of a percent, were sufficient to direct the flow of matter across billions of years. From these initial conditions, the first voids began to take shape, expanding as surrounding matter gathered into the earliest galaxies and proto-clusters. As time progressed, voids became more pronounced. Their interiors grew increasingly empty as matter flowed outward, guided by gravitational gradients toward dense filaments. Small fluctuations in density within the voids themselves persisted, allowing sparse galaxies to form in isolation, providing a record of early cosmic conditions. The boundaries of these voids became sharper, defining the edges of filaments and clusters, and creating the large-scale pattern now recognized as the cosmic web. The evolution of voids is both subtle and immense. Although they lack the luminous concentration of galaxies seen in clusters, their expansion exerts a measurable influence on surrounding structures. Filaments curve around voids, galaxies migrate along their edges, and the gravitational interplay between voids and dense regions shapes motion across vast distances. By studying the growth of these underdense regions, astronomers gain insights into fundamental forces and the distribution of both visible and dark matter, connecting the microcosm of primordial fluctuations with the macrocosm of the observable universe. In the context of cosmic history, voids are neither accidental nor insignificant. They are inevitable outcomes of the universe's earliest conditions, arising naturally from the initial irregularities imprinted in the primordial plasma. Their existence confirms that emptiness carries meaning, acting as a counterbalance to the concentrations of matter that form galaxies, clusters, and filaments. The ripples from the beginning, small as they were, have dictated the grand architecture of space, leaving behind the vast, serene expanses that define the large-scale cosmos. Through this lens, the formation of voids reveals the profound link between the smallest primordial fluctuations and the colossal structures spanning billions of light-years. What began as nearly imperceptible variations in density has grown into some of the universe's most defining features, showing that subtle irregularities can shape vast expanses of emptiness, guiding the flow of matter and directing the evolution of galaxies. These voids, far from being mere gaps, encode the history of cosmic growth, illustrating how minute early differences are magnified over eons into the intricate architecture that underpins the cosmic web. An unseen force pervades the cosmos, orchestrating the arrangement of galaxies and the immense expanses that separate them. Dark matter, undetectable through any form of electromagnetic radiation, exerts a gravitational pull that directs the assembly of cosmic structures. Its existence is revealed through the orbital speeds of stars within galaxies, the behavior of galaxy clusters, and the delicate bending of light known as gravitational lensing over immense distances. Absent this invisible component, the elaborate network of filaments, dense clusters, and expansive voids that form the cosmic web would not take shape in the strikingly complex patterns observed across the universe. Galaxies trace the contours of dark matter, assembling along its filaments where gravitational wells draw ordinary matter. Dense nodes arise where filaments intersect, concentrating mass and forming galaxy clusters that shine brightly across space. In contrast, regions with less dark matter provide less gravitational attraction, allowing these underdense areas to expand and become voids. Observations and simulations alike reveal that the growth of emptiness is intimately tied to the distribution of the invisible framework beneath it. Simulations of cosmic evolution offer profound insights into how dark matter sculpts the universe. Beginning with primordial density fluctuations, these simulations track the gravitational pull of dark matter over billions of years. Matter flows along emerging filaments, forming elongated structures and clusters, while voids expand as surrounding matter migrates toward higher density regions. The resulting patterns closely match observations, confirming that dark matter is a central architect in the shaping of both luminous structures and the vast empty expanses that punctuate the cosmos. Voids in particular demonstrate the subtlety of this influence. Their growth is not driven by an absence of force, but by the redistribution of mass around them. As galaxies accumulate along filaments and clusters, the low-density interiors of voids stretch in response, increasing in size and depth. This expansion is accentuated by the gravitational scaffolding of dark matter, which defines the pathways along which galaxies migrate and the boundaries that voids assume. Even sparsely populated voids contain traces of this underlying framework, with isolated galaxies often aligned along faint, residual filaments. Observational evidence underscores the link between dark matter and cosmic structure. Gravitational lensing, the bending of light from distant objects, reveals the presence of mass in regions otherwise empty to telescopes. These measurements confirm that dark matter is concentrated along filaments and around clusters, providing the skeleton that supports the visible universe. Its distribution governs the contrast between dense nodes and expanding voids, controlling the flow of matter on scales ranging from individual galaxies to superclusters. The evolution of the cosmic web reflects a dialogue between matter and emptiness. As filaments grow denser, voids expand, and the surrounding universe adjusts to maintain equilibrium. Dark matter does not act randomly, but provides a coherent framework, guiding the arrangement of galaxies and shaping the geometry of the web. The intricate balance between concentration and underdensity, between luminous clusters and expansive voids, is a direct consequence of this invisible influence. Understanding dark matter is crucial for comprehending how voids develop over time. Their growth rates, sizes, and internal structures are all governed by the gravitational pull of surrounding mass. Without dark matter, the web of filaments would be fragile, clusters less pronounced, and voids far less defined. By studying the interplay between the visible and invisible components of the universe, astronomers gain insights into the forces that dictate the cosmic landscape, revealing that emptiness is not merely a lack of matter, but a feature shaped by unseen fundamental influences. Through the lens of dark matter, the expansion of voids and the assembly of filaments become part of a coherent, predictable narrative. The invisible scaffolding molds the universe, orchestrating the movement of galaxies and the widening of voids, tracing patterns that stretch across billions of light years. This hidden force, unobserved directly yet profoundly influential, governs the growth of structure, demonstrating that the architecture of the cosmos is as much about absence as it is about presence. Over the vast timeline of the cosmos, cosmic voids are not static relics, but dynamic regions, growing and evolving as the universe expands. In their infancy, voids were subtle underdensities, minor deviations in a nearly uniform sea of matter. As gravity pulled surrounding material into denser filaments and clusters, these regions became increasingly empty, stretching across hundreds of millions of light years. Their expansion is a slow, continuous phenomenon, unfolding over billions of years, reshaping the large-scale structure of the universe. Observations of voids across different cosmic epochs reveal the gradual amplification of emptiness. Galaxies at the edges drift outward, pulled toward the more massive structures that dominate the web. This movement intensifies the contrast between dense filaments and underpopulated interiors, enlarging the voids and smoothing their interiors. The largest among them, known as supervoids, can encompass volumes larger than thousands of galaxy clusters, illustrating the immense scale over which cosmic evolution operates. The geometry of voids is shaped by both their surroundings and the intrinsic distribution of matter. Some voids are roughly spherical, while others assume elongated or irregular shapes, reflecting the influence of neighboring filaments and clusters. The boundaries of these voids are often marked by subtle gradients in galaxy density, a transition from emptiness to the luminous concentrations of the cosmic web. Within these regions, rare galaxies persist, forming sparse patterns that provide a record of the universe's formative conditions and the ongoing flow of matter. Dark matter continues to govern the expansion of voids. By shaping the gravitational landscape of the universe, it channels matter into filaments and clusters, leaving the interiors of voids to stretch and grow. The interplay between visible matter and dark matter dictates both the shape and rate of expansion, creating predictable patterns that can be modeled and compared to observations. Simulations demonstrate that voids merge over time, smaller underdense regions joining to form larger structures, a cumulative growth that mirrors the evolution of the cosmic web itself. The influence of cosmic expansion becomes even more pronounced when considering dark energy. As space itself stretches, voids experience accelerated growth relative to dense clusters. This differential expansion amplifies their scale, allowing emptier regions to occupy an increasing fraction of the universe. Observations of distant supervoids confirm this trend, showing that emptiness is not merely a passive consequence of matter migration, but a defining feature of cosmic dynamics shaped by both gravity and the mysterious repulsive effects of dark energy. Studying the evolution of voids provides insight into galaxy behavior and large-scale flows of matter. Galaxies at void boundaries often exhibit motions directed outward from the emptiest regions, guided by gravitational gradients. This motion affects their clustering, the shape of filaments, and the structure of superclusters. By examining void expansion over cosmic time, astronomers can infer properties of dark energy, the distribution of dark matter, and the rate at which the universe stretches, revealing how vast emptiness interacts with the luminous structures around it. The visualization of evolving voids offers a profound perspective on the universe. These regions, though sparsely populated, define the overall architecture of the cosmic web, shaping the motion of galaxies and the distribution of matter on the grandest scales. Their slow growth and merging illustrate a dynamic cosmos, where emptiness and structure coexist in an intricate balance. The study of voids across billions of years transforms our understanding of spatial geometry, revealing that the most unassuming regions, seemingly devoid of content, play a crucial role in the rhythm of cosmic evolution. By tracing the expansion of voids through cosmic history, it becomes clear that these regions are active participants in the universe's growth. They reflect the interaction between gravity, dark matter, and dark energy, demonstrating that emptiness is a fundamental agent in shaping the large-scale patterns we observe. The story of voids is not merely one of absence, but of persistent transformation, a slow unfolding of space that continues to influence the structure and motion of galaxies across the cosmos. The universe carries within it a force both subtle and pervasive, influencing the expansion of space itself. Known as dark energy, this mysterious component constitutes roughly 70% of the total cosmic content, driving the acceleration of the universe's growth. Unlike gravity, which pulls matter together, dark energy exerts a repulsive effect, stretching space and allowing the vast emptiness of cosmic voids to expand at an increasing rate. Its influence is most evident when examining the evolution of the largest voids, whose interiors grow faster than surrounding dense regions. Observations of distant supernovae provided the first compelling evidence for this accelerated expansion. By measuring the apparent brightness of these stellar explosions, astronomers discovered that galaxies are moving away faster than would be expected from gravity alone. The expansion is not uniform. Underdense regions respond more strongly to the stretching of space, causing voids to widen and deepen. Dense filaments and clusters resist this expansion slightly due to their greater gravitational pull, creating a contrast that shapes the large-scale geometry of the cosmic web. The interplay between dark energy and cosmic structure is revealed through detailed surveys and simulations. When mapped over billions of light-years, voids emerge as regions most sensitive to the repulsive effects of this energy. As filaments and clusters evolve along predetermined paths defined by dark matter, voids expand more rapidly, altering the trajectories of nearby galaxies and influencing the overall distribution of matter. This differential growth subtly reshapes the network, enhancing the prominence of emptiness while maintaining the coherence of the cosmic web. Cosmic microwave background measurements also provide insight into dark energy's influence. Slight fluctuations in temperature and density in the early universe have evolved under the combined effects of gravity and repulsive expansion, leaving an imprint on the large-scale distribution of galaxies. Voids act as amplifiers of these effects, their low-density interiors responding more readily to expansion, highlighting the relationship between empty regions and the fundamental forces shaping the cosmos. The dynamics of void expansion under dark energy affect more than just geometry. They influence galactic motion as well. Galaxies along the edges of voids are subtly accelerated outward, moving along the contours of filaments toward denser clusters. These motions provide indirect evidence for the presence and properties of dark energy, demonstrating how even regions nearly devoid of matter can offer critical insights into the behavior of the universe. In considering the cosmic web, the growth of voids under dark energy illustrates a broader principle. Absence can govern structure as powerfully as presence. As space stretches, voids expand silently, creating a landscape in which galaxies, clusters, and filaments are continuously reshaped. Dark energy's influence ensures that the universe remains dynamic on the largest scales, transforming emptiness into an active element that shapes motion, geometry, and the evolution of cosmic structures. Through this lens, the acceleration of voids is not merely an observational curiosity, but a defining feature of cosmology. It reflects the fundamental tension between the pull of gravity and the expansive influence of dark energy, highlighting how the emptiest regions of the universe respond to forces that govern the cosmos on its grandest scales. Even in seeming absence, the universe carries an imprint of energy, expansion, and transformation written across billions of light years. These regions act as magnifiers of cosmic dynamics, where the interplay of unseen forces becomes more evident, offering insight into the rate of expansion, the distribution of matter, and the underlying structure that shapes all observable phenomena across vast cosmic distances. Cosmic voids, vast regions nearly devoid of galaxies, are more than mere emptiness. They serve as profound windows into the nature of the universe. These immense expanses reveal how the interplay of matter, gravity, and dark energy shapes the large-scale structure of space. Light traveling through voids experiences subtle shifts caused by the low-density environment, offering astronomers a tool to measure the geometry of the cosmos and the behavior of fundamental forces. Photons passing through these regions may gain or lose energy slightly, tracing the contours of expanding space and providing a living record of cosmic evolution. The boundaries of voids are equally revealing. Galaxies at the edges respond to gravitational gradients, moving along the contours dictated by surrounding filaments and clusters. Their motions offer a map of how matter redistributes itself across billions of light years. Sparse galaxies residing within void interiors act as fossils of the early universe, preserving information about primordial fluctuations that guided the assembly of the cosmic web. Observing their distribution helps researchers understand the influence of dark matter, the shaping power of gravity, and the accelerating effect of dark energy. Voids illustrate a remarkable balance between presence and absence. Dense clusters display the aggregation of matter, while voids define the spaces through which these structures exist and evolve. The dimensions, shapes, and connectivity of voids reflect underlying physical laws, revealing the mechanisms governing both large-scale motion and the formation of galactic structures. These empty regions demonstrate that the architecture of the universe is not defined solely by matter, but also by the spaces between it. They highlight the essential role of absence in shaping patterns across cosmic scales. The internal dynamics of voids further emphasize their significance. While largely underdense, void interiors are not uniform. Subtle variations persist, allowing isolated galaxies to form in relative solitude. These galaxies trace faint filaments and interact weakly with surrounding structures, offering unique laboratories for studying galactic evolution without the interference of high-density environments. The interplay between low-density interiors and denser boundaries provides a natural contrast, enhancing our understanding of gravitational effects and matter distribution. Philosophically, voids challenge traditional notions of significance and presence. They show that emptiness is an active factor in cosmic evolution, guiding the motion of galaxies, influencing the growth of filaments, and dictating expansion patterns across vast regions. Their existence illustrates that the universe is defined as much by absence as by presence, and that spaces devoid of matter can hold crucial information about the forces that govern reality. These vast expanses, though seemingly barren, act as frameworks for cosmic order, subtly shaping gravitational flows, directing the formation of structures and providing natural laboratories where the interplay of dark matter, energy, and ordinary matter can be observed and understood in ways impossible in denser regions. In contemplating cosmic voids, the universe emerges not as a uniform continuum, but as a delicate balance between filled and empty regions, where structure and emptiness coexist. Every filament, cluster, and galaxy is contextualized by the void surrounding it, making these immense spaces integral to understanding the cosmos. By tracing the geometry, motion, and subtle contents of voids, astronomers gain insight into dark energy, dark matter, and the fundamental laws shaping space. Even in apparent emptiness, the universe conveys profound meaning, showing that absence is a force in its own right, sculpting the grand architecture of everything we observe. As our journey through vast cosmic voids, immense regions where galaxies grow rare and space stretches across millions of light years comes to a close, allow yourself to sink even deeper into relaxation. Picture those open expanses slowly expanding as matter gathers far away into distant clusters, leaving behind a calm and spacious stillness. Let your thoughts drift through this vastness, carried effortlessly across the quiet structure of the universe. Feel your thoughts gently fading, your muscles softening, and your breath flowing naturally and effortlessly. Rest here, fully supported in this safe and serene space. If you enjoyed this relaxing moment, please consider leaving a like, subscribing, and turn on all notifications so you don't miss any of our future videos. But for now, let your body relax, release any tension, and allow your mind to drift. Good night and sleep well.